Module 7, Lecture A, Text Features. By the end of this lecture, you will be able to convert dictionaries and text documents into Scikit-Learn feature matrices, configure tokenization, n-grams, vocabulary, stop words, and frequency controls, and build sparse text pipelines for classification tasks. Dictionary feature extraction. Dictionary vectorization. Dictionary vectorization converts records with named attributes into a numerical feature matrix for machine learning. Each dictionary becomes one observation, and its keys become consistent feature columns. This is important because most scikit-learn models work with numerical arrays or sparse matrices rather than raw dictionaries. Dictionary vectorization turns mixed data into a machine learning feature matrix. Numeric values are used directly, while categorical and Boolean values become indicator features, and missing keys are treated as absent. This makes it useful for irregular records and for text data after documents have been summarized into counts or attributes. Dictionary vectorization turns named features into a sparse matrix, which works well when most values are zero, as in categorical or text data. During fitting, it assigns each feature name to a fixed column and reuses that mapping for new data, so models interpret features consistently. This is especially important in classification pipelines, and also helps make predictions easier to understand by connecting columns back to the original feature names. Python code, dictionary vectorization. This example shows how Dict Vectorizer turns small dictionary records into numeric feature columns, making sparse features easy to represent and inspect. We import Scikit-Learn's Dictionary Vectorizer to turn dictionary data into numerical feature matrices for machine learning. We also import the Scikit-Learn library itself, so its tools and utilities, such as version checking, are available in the script. This example uses a collection of records, where each record describes one observation with attributes such as city, plan type, purchases, and discount status. The entries include different combinations, such as Paris or Tokyo, basic or premium plans, and optional discount information. This structure makes the data organized and easy to process for later analysis or transformation. A dictionary vectorizer in Scikit-Learn converts a list of dictionary records into a feature matrix for machine learning. It first learns the feature columns from the dictionary keys and values, then transforms each record into a row of data. Using sparse output, stores only non-zero values, making the matrix more efficient for large datasets with many features. The code verifies that the feature matrix has one row for each input record. If the counts do not match, it raises an error because the vectorization did not preserve the expected one-to-one mapping. This check helps confirm that all input data was transformed correctly. The code checks the results of the vectorization process by showing the Scikit-Learn version, the size of the feature matrix, and the generated feature names. This helps confirm that the transformation worked correctly and makes it clear what each column in the matrix represents. The sparse feature matrix is converted into a dense array, so its values are easier to inspect. The array is then changed to integer values for simplicity, and the first row is printed. This shows the numeric features created from the first dictionary record, and helps confirm how vectorization transformed the original data. A new record is created as a dictionary containing fields such as city, plan, and purchases. The vectorizer then transforms this record using the feature structure it learned from the original data, so the new observation matches the same numeric format. The transformed result is displayed as a clear list of integer values, showing how the new data fits into the existing feature space. This script shows how Scikit-Learn's Dictionary Vectorizer converts dictionary-based records into a numerical matrix for machine learning. Each record's keys become feature columns, and values, such as categories or numbers, are encoded consistently across all records. The output includes the matrix shape, feature names, and a dense view of the encoded data, while new records are transformed using the same columns. This is a common way to prepare categorical dictionary data for machine learning models. Feature hashing. Feature hashing converts dictionary-style features into a fixed-size numeric matrix without building a full vocabulary. Instead of assigning each feature name its own stored column, it uses a hash function to choose the column, so new feature names can be processed immediately. This is useful for fast-changing data, such as online advertising features, because the matrix shape stays consistent without rebuilding feature mappings. Feature hashing is an efficient way to turn large or streaming datasets into sparse numeric features without storing a full mapping from feature names to columns. Each record is transformed independently, with active features placed in positions determined by hashing. This works well for data with many unique keys, such as product IDs or user tags, and produces a sparse matrix that can be used directly by machine learning models. Feature hashing maps many possible feature names into a fixed set of numeric columns. With enough columns, important signals usually stay distinct enough for the model to learn useful patterns, even without knowing the original feature names. This makes it well-suited for large, changing production systems, where maintaining a traditional vocabulary is difficult. Python code feature hashing. Feature hashing converts dictionary record features into a fixed set of numeric columns by hashing each feature name. The result is a sparse numeric matrix that can be used for machine learning. We import Scikit-Learn for machine learning and data processing tools, then use its feature hasher to turn categorical data into a fixed-size numeric matrix. This feature hashing approach is useful for efficiently handling high-dimensional data without storing a full vocabulary. The data is organized as a collection of user event records, where each record stores categorical features such as location, browser, and action. Each feature is represented by a text label paired with the value 1, showing that the feature is present. This format prepares the categorical data for feature hashing, which converts it into a fixed-size numeric representation. A feature hasher is created to convert dictionary-based event data into 8 hashed features. With alternate signs turned off, the hashed values keep the same sign. Transforming the event dictionaries produces a sparse matrix, where each row is the hashed feature representation of one event. We first set the expected size of the hashed matrix using the number of events and the 8 selected features. Then, we compare the actual matrix size against that expectation. The code makes a sparse matrix easier to inspect by converting it into a dense NumPy array using the toArray method. It then changes the values to integers with the asType int method. This is mainly useful for displaying small matrices in a more readable form. The output checks that feature hashing worked as expected. It reports the Scikit-Learn version for reproducibility, the number of input records, and the shape of the hashed matrix to confirm the expected dimensions. It also shows how many non-zero values appear in each row, indicating how sparse each event representation is. For this small example, the sparse matrix is converted to a dense form, so the hashed features can be inspected directly. This script shows how Scikit-Learn's feature hasher converts user event dictionaries, such as city and browser attributes, into a fixed-size sparse matrix. It reports basic checks like the Scikit-Learn version, input count, matrix shape, and non-zero values per row to confirm the hashing worked as expected. It can also display the dense version of the matrix, illustrating how feature hashing represents high-dimensional categorical data without storing a vocabulary. Hashing trade-offs. Feature hashing converts dictionary-like data into a fixed-size feature matrix by hashing each feature into a column instead of building and storing a full vocabulary of feature names. This makes it useful when features are very large, sparse, or appear unexpectedly, such as in online advertising. The trade-off is that the resulting columns are not human-readable, so it is harder to interpret which original features affected a prediction. Feature hashing can cause collisions, where different features share the same column. This is expected when compressing many possible features into fewer hash buckets. With enough buckets, collisions are uncommon and model performance usually remains strong. But too few buckets can mix unrelated signals and hurt learning. The key is to choose a bucket count that balances efficiency with information loss. Feature hashing is useful for production and streaming systems because it transforms new data consistently without needing a stored vocabulary. This makes it well-suited to settings where features change often and retraining is difficult. Its main drawback is reduced interpretability since original feature names are not preserved. In general, use feature hashing for scalability and deployment simplicity, and dictionary vectorization when feature inspection and explanation matter most. Text vectorizers. Count vectorizer basics. A count vectorizer turns text into numbers by counting how often each distinct term appears in each document. This creates a feature matrix where terms are columns and documents are represented by word counts. This bag of words approach ignores word order and grammar, but it is simple and useful for early text analysis. Count vectorization turns text into a feature matrix that statistical models can use. Each document is represented by word frequencies, allowing models to learn patterns such as terms linked to sentiment or spam. It does not understand meaning, but it is effective for tasks like text classification and sentiment analysis. Count vectorizers often produce sparse matrices because each document contains only a small subset of the full vocabulary. Sparse storage keeps only the non-zero word counts, which makes large text datasets easier to manage. The vocabulary is learned from training data and then used on new documents, so unfamiliar words may be ignored. Count vectorization captures word frequency, but not word order or deeper meaning on its own. Python code. Count vectorizer basics. This example shows how short texts can be converted into word count features. The count vectorizer learns the vocabulary from the training documents, then represents each text as sparse counts with corresponding feature names. We import pandas for working with structured data, then use Scikit-Learn's count vectorizer to turn text documents into token count matrices. This prepares text data for common natural language processing tasks. We begin with a small set of short text documents to build a vocabulary for text analysis. The sentences cover refund offers, urgent refund requests, slow service, friendly service, and good food. Keeping the documents simple makes the resulting vocabulary easier to inspect and understand. A count vectorizer from Scikit-Learn converts text documents into numerical features. In this setup, it ignores common English stop words and uses both individual words and two-word phrases to capture more context. Applying the fit and transform process learns the vocabulary from the documents and produces a count matrix, where each row represents a document and each column represents a word or phrase feature. The code verifies that the count matrix has one row for each document. If the row count does not match the number of documents, it raises an error. This check helps confirm that the document-to-matrix transformation was done correctly and that the data structure is consistent. The code gets the vectorizer's learned feature names, which represent the document vocabulary. It then defines a small set of target terms, such as refund, service, free refund, and slow service, to focus later analysis or reporting on specific parts of that vocabulary. We identify the positions of selected terms in the feature names, then use those positions to keep only the matching columns from the count matrix. This smaller matrix is converted into a dense array and placed into a pandas data frame. The result is a compact, readable table showing counts only for the chosen terms. The code summarizes the output of a count vectorizer by reporting the learned vocabulary size, the count matrix dimensions, and the number of non-zero entries in the sparse matrix. These checks show how many terms were extracted, how they map across the documents, and how often they appear. It then converts the small count matrix into a readable pandas table, so the selected term counts are easier to inspect. This script shows how Scikit-Learn's count vectorizer turns short text documents into numerical word count data. It removes common English stop words, includes both single words and two-word phrases, and builds a sparse matrix where each row is a document, and each column is a learned term. The code verifies the matrix size, then displays key results, such as the number of features, the matrix shape, non-zero counts, and selected term counts for words like refund and service. Token controls. Token controls determine how text is broken into units, such as words or character sequences, before a vectorizer turns it into numerical features. This step shapes the vocabulary the model can learn from, so it is central to feature extraction. Default tokenization often lowercases text, removes punctuation, and splits on word boundaries, which works for many tasks, but not all. In specialized domains or social media, capitalization, symbols, or emojis may carry meaning, so token controls help define what should count as meaningful text. Token control means choosing which text patterns count as tokens for a task. Vectorizers often ignore very short fragments and punctuation to reduce noise, but this can remove useful short terms. Choices about contractions, apostrophes, and lowercasing can also affect meaning, especially in sentiment analysis, names, and acronyms. The goal is to make tokenization match the language patterns that matter for the specific task. Token controls shape the size, sparsity, and usefulness of a feature matrix. Loose tokenization can create too many rare, noisy features, while overly strict tokenization can remove important signals. For example, dropping numbers or symbols may lose details such as error codes or email addresses. Good token control balances technical choices with domain knowledge, so the vectorizer captures meaningful distinctions. Python code, token controls. This example shows how token controls in vectorizers affect text processing. Token patterns determine which parts of the text are counted, which changes the resulting vocabulary and matrix output. We import pandas to work with tabular data, then use Scikit-Learn's count vectorizer to turn text documents into token count data. This lets us measure how often terms appear in the text for later analysis. A small set of 3 short documents is created to test how vectorizers split text into tokens. The documents include technical terms, abbreviations, special characters, numbers, single letters, and hashtags. This helps show how default tokenization may remove some tokens, while custom token patterns can keep them. A count vectorizer with default settings converts text documents into token count features. When applied to the documents, it learns the vocabulary and produces a sparse matrix showing how often each token appears, using the default rules for identifying words. A custom Scikit-Learn count vectorizer is configured with a token pattern that captures single-letter words and hashtag terms, which the default settings might miss. It is then applied to the documents to convert them into a token frequency matrix based on these custom tokenization rules. We compare the vocabularies learned by the default and custom vectorizers by retrieving each one's feature names. This shows which tokens each token pattern identifies from the same documents, making it clear how the token pattern changes the extracted vocabulary. We choose a small set of tokens to examine, such as AI, C3, app_v2, and urgent. Then we compare them with the custom vectorizer's vocabulary and keep only the ones that actually appear there. This filtered set makes the final matrix easier to read and focused only on relevant tokens. Create a list to store the vocabulary positions of the tokens you want to examine. For each visible token, find its matching index in the custom vectorizer's vocabulary and save it. These saved indexes identify the relevant columns in the token matrix, so you can focus on those parts of the data later. The code selects the columns for the chosen tokens, creating a smaller matrix with only the relevant data. It then converts that matrix into a standard array and builds a pandas data frame with columns labeled by the visible tokens. This presents the selected token occurrences in a clear table for easier reading and analysis. This demonstration shows how token control works with Scikit-Learn's count vectorizer. It compares the tokens found by the default pattern with those found by a custom pattern, then reports the vocabulary size for each approach. Finally, it prints a small count matrix in a readable table format, so the selected token counts can be inspected. This script shows how changing the vectorizer's token pattern changes the vocabulary and feature matrix created from text documents. The default pattern keeps words with at least 2 characters, while a custom pattern also captures single-letter words and hashtags, producing a larger vocabulary. It then focuses on selected tokens such as AI, C, and urgent to create a simpler matrix showing their counts in each document. The main point is that token patterns strongly influence which text features are included in analysis. N-gram features. N-gram features improve a bag of words model by treating short sequences of tokens as features, not just individual words. A unigram is 1 token, a bigram is 2, and a trigram is 3. Including n-grams helps capture local word order and phrase meaning, such as when word combinations carry meanings that single words miss. This gives machine learning models a more informative feature matrix. Choosing an n-gram range balances simplicity against detail. Single words keep the feature space smaller and often work well for small datasets or broad topics, while 2 or 3 word phrases can capture more specific patterns for tasks like sentiment analysis or spam detection. Longer phrases can greatly increase memory use and training time, so they are usually combined with vocabulary limits and frequency filters to keep only useful terms. N-gram features depend heavily on how text is tokenized and how stop words are handled. Removing common words can improve efficiency, but it may also break important phrases or lose signals like negation and intent. The best choice depends on the language, domain, and data size. Overall, n-grams help classifiers capture short word patterns, offering a useful middle ground between simple word counts and deeper language analysis. Python code, n-gram features. This example compares unigram and bigram text features. It shows how n-grams capture short word order patterns and how adding phrase features changes the size of the feature matrix. We import Scikit-Learn's count vectorizer to turn text into token count matrices for natural language processing tasks. We also import the full Scikit-Learn library to access its broader tools, such as version checks and other utilities needed later. This example uses a small set of short text reviews to study sentiment and text features. The reviews include negative phrases like "not good service" and "not fast shipping," along with positive phrases such as "good service" and "fast shipping" and "good product." Their simplicity makes it easier to see how negation and word order can change the meaning of a review. We use Scikit-Learn's count vectorizer to count single words or unigrams in a set of documents. After fitting it to the text, it converts the documents into a matrix, where each row is a document and each column is a unique word. The values show how often each word appears, making the text easier to analyze at the word level. To capture both single words and short phrases, use a count vectorizer set to include one-word and two-word sequences. After fitting it to the documents, each document becomes a row in a matrix, with columns representing either individual words or adjacent word pairs. This gives the model a richer view of the text by including common word combinations. The code verifies that the unigram matrix has one row for each document. If the counts do not match, it raises an error, signaling a problem in the transformation. This check helps ensure that feature extraction correctly represents every document and preserves the data structure. The code verifies that the bigram matrix has one row for each document. If the number of rows does not match the document count, it raises an error, signaling a problem in how the matrix was built. This check helps confirm that the transformation preserved the correct document-to-row mapping. We first check the Scikit-Learn version to support reproducible results. Then, we compare the shapes of the unigram and bigram feature matrices, showing how adding adjacent word pairs increases the number of text features. We first get the feature names from the bigram vectorizer, which include the unique words and word pairs found in the documents. Then we focus on selected bigram features, such as not good, good service, and fast shipping, to see how often these meaningful phrases appear. This helps capture patterns that single words alone might miss. The process checks each selected bigram feature, finds its matching column in the vectorized feature list, and extracts that column from the bigram matrix. These values show how often the bigram appears in each document. The counts are converted into a simple list, then printed with the feature name for easy inspection. The code checks whether the phrase not good appears among the feature names. If it is present, the bigram vectorizer has captured that negation phrase as a feature, helping the model represent the meaning of negation in the text. This script shows how n-grams can represent text features using Scikit-Learn's count vectorizer. It compares unigrams, which count individual words, with bigrams, which also include adjacent word pairs, and therefore create more features. The key point is that bigrams can capture meaningful phrases such as not good and fast shipping, including patterns like negation that single word counts may miss. TF-IDF, text pipelines. TF-IDF, transformation. TF-IDF is a way to turn text into numerical features for classification by giving more weight to words that are important in one document but uncommon across the whole collection. This helps reduce the influence of frequent but less useful words, such as the or please. In tasks like customer support classification, TF-IDF highlights more informative terms, such as refund or password, so the model can better distinguish between categories. In text classification, TF-IDF is usually applied after tokenization and vocabulary building to create a sparse feature matrix for classifiers. Sparse storage is efficient because each document uses only a small part of the full vocabulary, leaving many zero values. TF-IDF also gives more useful weights to words, reducing the impact of very common terms and highlighting words that better distinguish one document type from another. TF-IDF helps text classifiers generalize by reducing the influence of common, less useful words and emphasizing more distinctive terms. This is especially useful when new documents differ from the training data, such as in email filtering. Although TF-IDF does not understand grammar or intent, it works well with linear classifiers and provides a strong foundation for text classification when paired with good preprocessing and vocabulary selection. Python code, TF-IDF transformation. This script shows how TF-IDF supports text classification by giving more weight to distinctive words and less weight to common ones. A sparse text processing pipeline then uses these weighted features to predict message categories. We import key Scikit-Learn tools for building and evaluating a text classification model. The TF-IDF vectorizer turns text documents into numerical features. Logistic regression predicts categories, and the accuracy score measures how well predictions match the true labels. We also use a train-test split to separate data for training and evaluation, and a pipeline to combine the processing and modeling steps into one streamlined workflow. We define a small set of labeled customer service messages to use as training examples. The messages cover delivery and refund issues, password and account problems, and subscription or billing questions. This prepares the data for a model that can learn to classify similar messages by their content. The dataset assigns each message to one of three issue categories: delivery refunds, password or account problems, and subscription billing questions. Each category appears multiple times, so the model has examples of every type. These labels are used to train the model to classify new messages into the correct predefined category. We split the text data into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, and a fixed random state makes the split reproducible. Stratifying by the labels keeps each category proportionally represented in both sets, which supports fair model evaluation. This pipeline classifies text by first turning it into numerical features with a TF-IDF vectorizer, which removes common English stopwords and uses both single words and bigrams. A logistic regression model then learns from these features to make predictions. The setup combines text transformation and model training into one reproducible workflow. The pipeline learns from the training texts and labels by converting the text into TF-IDF features and training a logistic regression classifier. It then predicts categories for the test texts, and the accuracy score compares those predictions with the true labels to measure performance. We inspect the TF-IDF step in the pipeline to understand how it converts text into numerical features. The training texts are transformed into a sparse matrix of TF-IDF values, where each column represents a learned term. Retrieving the feature names lets us interpret those columns and connect the numbers back to the original vocabulary. To find the most important TF-IDF terms in a test message, the message is first transformed with the pipeline's TF-IDF step into a numerical representation. The non-zero entries show which terms appear in the message. These terms and their TF-IDF scores can then be collected to identify the words that have the strongest influence. For each non-zero term in the example matrix, we identify its feature name and match it with its TF-IDF score. This score shows how important that term is within the specific test message. The resulting term score list collects each term with its significance for later analysis. The code ranks terms by their TF-IDF scores from highest to lowest, so the most important terms come first. It then selects the top 5, which are likely the most distinctive words in the text, and the strongest contributors to classification. The output summarizes key checks and results for a text classification model. It reports the Scikit-Learn version, the size and sparsity of the training TF-IDF data, and the model's test accuracy. It then shows one test example, highlights its most important TF-IDF terms, and gives the predicted category to illustrate how the model makes a classification. This script shows how to classify text messages using TF-IDF features and logistic regression. It splits a small labeled dataset into training and test sets, trains a pipeline that converts text into numerical features, and predicts categories such as delivery refunds, account passwords, and subscription billing. It then reports accuracy and basic model details, and highlights the most distinctive terms in one test message to help explain the predicted category. Vocabulary limits. In TF-IDF text pipelines, vocabulary limits control which words become model features. They keep the feature matrix smaller and less noisy, which can speed training and reduce sensitivity to random patterns. The goal is to keep useful terms, such as words that distinguish support categories, while dropping low-value items like rare misspellings or unique order numbers. Vocabulary limits help a text classifier focus on useful words instead of noise. A maximum vocabulary size keeps the most important terms, while minimum frequency removes rare words that may be errors or irrelevant. And maximum frequency removes words that are too common to distinguish classes. Together, these settings help the model use terms that are informative without being too broad or too narrow. Vocabulary limits should be chosen based on dataset size, language complexity, and the goals of the classification task. Rare words may be important in some domains, so these limits should be treated as tunable settings rather than fixed rules. Testing different vocabulary sizes helps balance model performance, interpretability, and efficiency, while keeping the text representation compact and informative. Python code, vocabulary limits. This script shows how vocabulary limits affect TF-IDF text pipelines. It uses frequency thresholds to decide which text features are kept. Then, compares a small classifier with limited and unlimited vocabularies. The script imports key Scikit-Learn tools for building a text classification model. It uses a TF-IDF vectorizer to turn text into numerical features, logistic regression for binary classification, and an accuracy metric to evaluate predictions. It also imports a train test splitting tool to separate training and evaluation data, plus a pipeline tool to combine pre-processing and modeling into a cleaner workflow. This example creates a small set of support ticket messages for testing text classification. The messages use category-specific words for billing, shipping, and account issues, such as refund, delivery, and login. This simple dataset helps show how different vocabulary limits can affect classification results. A set of labels assigns each support message to a category such as billing, shipping, or account. These labels match the messages in the dataset and serve as the target values for training the machine learning model to predict ticket categories from text features. We split the documents and labels into training and testing sets using Scikit-Learn's train test split. This keeps vocabulary learning limited to the training data, reducing overfitting. 1/3 of the data is reserved for testing, a fixed random state makes the split reproducible, and stratification preserves the label balance in both sets. The pipeline combines two main steps for text classification. First, a TF-IDF vectorizer converts the training text into numerical features using all available tokens. Then, a logistic regression classifier learns patterns from those features, with up to 200 iterations to help it converge. This pipeline turns text into TF-IDF features, and then trains a logistic regression model. The vectorizer keeps terms that appear in at least 2 documents, but not in more than 85% of documents. And it limits the vocabulary to the 8 most important features. This removes very rare or overly common words, helping the model focus on useful patterns while staying simple. The logistic regression model is allowed up to 200 iterations to help it converge. Both the wide and limited pipelines are trained on the same text examples and labels, so their results can be compared fairly. The wide pipeline uses all available features, while the limited pipeline uses a smaller feature set. This comparison shows how vocabulary size affects model performance. We compared 2 text classification pipelines by looking at the vocabulary each TF-IDF vectorizer learned and then measuring test accuracy. The wide pipeline uses all available terms, while the limited pipeline uses a smaller vocabulary shaped by frequency constraints. Comparing their accuracy shows how vocabulary size affects model performance. The output first reports the Scikit-Learn version to support reproducibility. It then compares the full vocabulary with the restricted vocabulary, showing how many terms are kept and which terms remain after limiting. Finally, it compares the two models' test accuracy, rounded to 2 decimal places, to show how vocabulary size affects performance. This script shows how limiting vocabulary affects text classification with TF-IDF and logistic regression. It classifies support tickets as billing or shipping, then compares a model that keeps all tokens with one that keeps only moderately frequent terms. The limited model uses far fewer features while still achieving competitive test accuracy. This demonstrates the trade-off between vocabulary size and performance, and why feature selection matters in text classification. Sparse text pipeline. A sparse text pipeline turns raw documents into numerical features, often using TF-IDF to emphasize important terms. Because most feature values are 0, the data can be stored as a sparse matrix, saving memory on large text collections. Keeping this sparse format through the classifier lets the system learn useful patterns while representing messages compactly. A sparse text pipeline keeps training and prediction consistent by using the same text processing steps throughout. It learns how to tokenize text, apply TF-IDF weighting, and train a classifier. Then, applies those same rules to new documents. This keeps new data aligned with the learned vocabulary, so the model interprets features correctly when classifying text into predefined topics. Sparse text pipelines make text modeling more reliable by combining transformation and classification into one workflow. This lets cross-validation evaluate the full process, including tokenization and TF-IDF weighting, rather than only the final classifier. By keeping feature extraction inside the pipeline, they help prevent evaluation data from influencing training and support fair, organized model comparison. Python code sparse text pipeline. Build a sparse text classification pipeline using TF-IDF to keep text features memory efficient. When making predictions, reuse the same learned vocabulary so new text is represented consistently. This setup imports the main Scikit-Learn tools needed to build and evaluate a text classification model. A TF-IDF vectorizer converts text into numerical features, logistic regression predicts the text categories, and an accuracy measure checks how well the predictions match the true labels. The data is split into training and testing sets, so performance can be measured on unseen examples. And a pipeline combines the text transformation and classifier into one workflow. We define a small, labeled set of customer support messages, where each short text represents an inquiry. The labels cover categories such as billing, technical issues, cancellations, and general questions. This self-contained dataset can then be used to train a model to classify new messages by their content. A set of labels assigns each support message to a category such as billing, technical help, cancellation, or general support. These labels match the earlier messages and provide the training data a model needs to learn how to classify new support requests by their content. The text data and labels are split into training and testing sets using Scikit-Learn's train-test-split function. 1/3 of the data is kept for testing, and a fixed random state makes the split reproducible. Stratifying by label keeps the class proportions balanced in both sets. A text classification pipeline combines feature extraction and modeling in one consistent workflow. It first converts text into TF-IDF features, using both single words and word pairs while removing common English stopwords. A logistic regression model then learns to classify the text from those features, with settings chosen to support convergence and reproducible results. This pipeline makes training and transforming the data more efficient and reliable. Fitting the pipeline means training it on the labeled text data. The text is first converted into TF-IDF features, and then the logistic regression model learns how those features relate to the categories. This step is essential because it captures patterns in the training set that the model can use to classify new, unseen text. The code converts the training texts into a sparse TF-IDF matrix, which stores only non-zero values to save memory with large text data. It then verifies that the matrix reports its number of non-zero entries. If not, it raises an error, confirming that the TF-IDF step produced the expected, efficient sparse format. The pipeline predicts labels for the test texts using the same TF-IDF settings learned during training, keeping the feature representation consistent. The accuracy score then compares these predictions with the true test labels to measure how well the model performs on unseen data. To classify new text messages, we provide the trained pipeline with messages it has not seen before and ask it to make predictions. The pipeline applies the same TF-IDF transformation and logistic regression model learned from the training data. It then returns a predicted label for each message based on the patterns it learned. The output checks the Scikit-Learn version for reproducibility, then summarizes the TF-IDF matrix by showing its size and number of non-zero text features. It also reports the model's test accuracy on unseen data and shows predictions for new messages, demonstrating that the same pipeline can classify new text. This script creates a Scikit-Learn text classification pipeline for support messages labeled as billing, technical, cancellation, or general support. It uses TF-IDF features with logistic regression, keeping the feature matrix sparse for efficient memory use, and splits the data with stratification to preserve category balance. After training, it reaches about 75% test accuracy and predicts categories for new messages, such as billing or technical issues. It also reports basic details like the Scikit-Learn version, matrix shape, non-zero values, accuracy, and predictions. In this lecture, you learn to convert dictionaries and text documents into Scikit-Learn feature matrices, configure tokenization, n-grams, vocabulary, stopwords, and frequency controls, and build sparse text pipelines for classification tasks. In the next lecture, Lecture B, we will go over images custom.
Thank you for your attention. See you all in the next lecture.